Hello guys, welcome back to another video. I hope you all are doing well. Today we'll be solving the 28th problem of the Blind 75 series. The problem is course schedule. The problem statement is there are total num courses you have to take label from 0 to num courses minus 1. You are given an array prerequisites where prerequisites of I is equal to AI comma BI indicates that you must take course BI first if you want to take course AI. For example, the pair 0 comma 1 indicates that to take course 0 you have to first take course 1. Return true if you can finish all the courses, otherwise return false. Guys, the question states that you will be given a integer num courses as an input, and in this variable num courses, you will be given the total number of courses that you have to finish. Okay, so if the value of num courses is 5, the courses will be labeled from 0 to 4. And if the value of num courses is n, so the labeling of the courses will be from 0 to n minus 1. That is what you are given over here in the first line. Okay, so whatever the number of courses are there, the labeling of those courses will be from 0 to total number of courses minus 1. And apart from this, you are given a 2D array that is prerequisites. And in this prerequisites, you are given some conditions which you need to follow or which need to be satisfied while you are opting for these courses. Okay, so let's understand this question more clearly with the help of an example. Okay, so if we see the first example that we are given over here, we can see that uh, the number of courses that we are given is 2. Okay, so if there are two courses, those two courses will be labeled as 0 and 1 as we are given in the condition above. Okay, so we have two courses 0 and 1, and the prerequisites is in the prerequisites array we have a pair 1 comma 0. So this 1 comma 0 represents that uh, you have to finish the course 0 first, then only you can go for the course 1, right? So you need to tell by satisfying all these conditions in the prerequisites array, can you finish up all these courses that are given to us? And here we can definitely finish because we have two courses 0 and 1. What I will do, I will first finish the course 0, and once I have finished the course 0, then I will simply go for course 1 and I will finish that. So in this way, I by fulfilling all the conditions that are given in the prerequisites array, I can complete all the courses that are given to us. Okay, so that is why we have returned true over here, right? Now let's move to the second example. In the second example, again we have two courses. So if there are two courses, those two courses will be labeled as 0 and 1. Okay, so what are the conditions that we are given over here? So in the prerequisites array, we have two conditions. The first one is 1 comma 0. So 1 comma 0 represents that this 0 should be finished before 1. Okay, so it means I have to finish the course 0 first, then only I can go for course 1. Okay, I can represent it like this. Okay, but there is one more condition over here. In the second conditions, we are given the just opposite condition. We have, instead of 1 0, we have 0 1. It means I have to finish course 1 first, then only I can go for course 0. Okay, so at first I have to finish the course 1 in this given prerequisites array. Sorry, uh, in I have to finish the course 1 first, then I have to go for course 0. So the condition is exactly opposite of the first condition. Okay, so here we know that as we have the cyclic dependency among the courses that are present, the first condition says that 0 should be finished before 1, and the second condition says that 1 should be finished before 0. Okay, so these two are like contradicting each other. So we cannot, fulfill both of these conditions together. So that is why in this case, I cannot get any linear ordering of all the courses that I can follow to satisfy all the conditions. So that is why in this case I have written false as we are given over here. Okay, so now moving towards the solution of this problem. So what I will do, if I represent all the courses that we are given to us as a nodes of a graph, and I can represent the condition, these prerequisite conditions by edges of a graph. What I will do, I will form a directed graph for this particular uh, problem, and whatever the prerequisite conditions are there, I will be representing those prerequisite conditions by the edges of that directed graph. And once I will be able to transform this problem into the graph problem, then I can use the techniques and algorithms of a graph to solve this problem. Okay, so what I will do, I will transform this problem into graph. Once this problem will be converted into graph, then I simply need to check whether there will be any linear ordering possible for the vertices of that graph. Okay, let's write down the code for this particular approach. Okay, so once you will be able to transform this problem into graph, then you simply need to check in that particular directed graph, can you find the linear ordering for that particular directed graph, which satisfy the condition that, if there is an edge from vertex u to v, in that linear ordering u should appear before v. Okay, so you can do that this particular thing by using two techniques. You know that the linear ordering is possible only if the graph is directed acyclic graph. Okay, so we will be making the directed graph for sure. So you just need to check whether there is cycle present in the graph or not. Okay, so you can use the cycle detection algorithm to check whether we have the cycle in the directed graph that we will form or not. But here I will be using the topological sort method, because the reason is we have a follow-up question after that, that is the core schedule 2. So the core schedule 2 is exactly same question, but here we have just one extra condition over here, that apart from just telling whether you can finish all the courses or not, you have to also tell the sequence in which the sequence that you will follow in order to finish all the courses. So if you will use the topological ordering method, you can solve both these questions, course schedule 1 and course schedule 2, by exactly same method. Okay, so that is why we will be using the topological sort method. But you can also solve this course schedule program, sorry, course schedule question by using the cycle detection in the directed graph method. Okay, now let's write down the code for this approach. So the first step is to create a graph for this given problem. Okay, so we know that for creating a graph, either we use the matrix representation or the adjacency list representation. So here I will be using the adjacency list representation. So the total number of vertices in the graph will be equal to the number of courses that we are given over here. Okay, so what I will do, I will create a adjacency list, that is array of vectors of size v. Okay, now what I will do, I will traverse this prerequisites array, and according to these prerequisites array, I will define the edges in this particular graph. And we know that, as it is a 2D vector, so all the elements of in each index of this 2D vector, I will be having a vector that consists two elements. Okay, so as we are given over here, we will be having two elements, ai comma bi. So ai comma bi indicates that you must take bi before ai. Okay, so that means we can represent this like there is an edge from bi to ai. So the first element of this vector, I will store that in the variable named as a, and the second element will be stored in another variable named as b. And we know that there is an edge from B to A according to this given condition that you are given over here. So what I will do, I will push this particular A in the vector that is corresponding to A. Sorry, in the vector that is corresponding to B in the adjacency list. Okay, so in this way, I can create a graph for this particular problem. So once we are done with the graph, now we can use the topological sorting algorithm to find out whether there is a linear ordering possible for this particular graph or not. Okay, so uh, let's create a vector to store a topological ordering. Let me call this as topo. And initially, the first step of uh, finding the topological ordering is to create a in degree array. Okay, so we have to find the in degree of all the vertices present in the graph. So let's create a vector name, and I will name this as in degree, and this in degree will contain the in degree of all the vertices that are present in the graph. Okay, so in degree is basically the number of incoming edges towards all the number of incoming edges towards a particular vertex. So that value will be stored in this in degree array for all the vertices that are present in the graph. For calculating the in degree, what I will do, I will traverse this given graph, and I will check the neighboring nodes for each vertex or each node that is present in the graph. And if this particular node it is neighboring of any other vertex, it means there is an edge from that particular vertex to this particular vertex. So if this happens, I will increase the integrity of this it. Okay, so in this way I can calculate the integrity of all the vertices that are present in the graph. Now I will start a while loop while q is not empty. Like, we will do the similar kind of steps that we do in the PFS. So I will pop out the front node, and whatever node that we have popped out, I will store in the topological ordering. Okay. Now after that, what I will do, I will reduce the integrity of all the adjacent node of this particular node. Uh, okay, I will check out all the adjacent node for this particular node, and I will reduce the integrity of all these nodes. And after reducing the in degree, I will check if in degree of this it has become 0. So if this condition becomes true, what I will do, I will push this particular node into the queue. Okay, so finally, when this while loop will be over, I will be having the topological ordering in this vector named as topo. So after that, what I need to do, so if there will be valid topological ordering possible, and if it would be possible to find out the topological ordering for this particular graph, so the size of this particular vector topo will be equal to the number of vertices in the graph. Okay, so I will check if the size of this particular vector is equal to the number of vertices present in the graph. If this is true, I will return true. Okay, otherwise it means the valid topological ordering is not possible for this particular graph. So that in that case I will simply return false. Okay, so let's try to run this code. Oh, sorry, it will be vector of 1. I have mistyped this. Okay, now the sample test cases have passed. Now it's working fine. Let's try to submit this solution. And yes, guys, it got accepted. So in this way, you can solve this given problem, and the link of the codes will be given in the description. You can check out the GitHub repository link. And that is all for today's video. We will meet in the next video. Bye bye.